Same I diffusion, you keep it as it is, huh? Because they're going to help us a lot. Okay, now we'll start with this. Now come for this one. So as I increase the reverse bias, there's a positive terminal connected to n-type. What it does, it will directly pull the electrons here, no? And what this negative terminal do, it will inject electrons into the p-type. So first we'll discuss the flow of charges here. So here this electron, the positive terminal will directly pull the electron. So this electron will come here. This electron will come here. I think, see, there's the only way what we know to analyze the concept. Take help of electron. It'll be much easier for you than all. So here, so simplest way, this electron will take this position. Let's assume that one. This electron will take this position. So this electron will take this position. So now what will happen to majority carriers here? So shall I say they're moving away? So in what direction the electrons will be moving here? In this direction. Or majority carriers, if you want, you can write the majority carriers. They'll move away from junction. And similarly, the hole, I say that they'll move towards left. Sir, how come? Okay, let's take this one. This will push electron. This electron, what it will do, it will go and occupy at this position of the hole. If a hole captures electron, what do we get? We get valence electron and we don't show it, no? This electron has come here. Now what this hole will do, will pull out this valence electron. So now it has come. So look at the position of hole. So earlier I'm explaining this, try to remember. This electron, what when the moment it arrives will be captured by hole, because the electron will become minority carrier, will be captured by hole. So if a hole captures electron, we'll get valence electron, and that valence electron we don't show it. Take it out. Now this valence electron, what happen, will be pulled by the hole. So therefore now the hole, what happen, will take this position. So here will be like this. Here what you see, that the majority carriers, they'll move away from junction. The holes will move away from junction. The electrons will move away from junction. Then what will happen to the ions? So these ions, so shall I say, they're being, don't say robbed off, they're being depleted. Again, they're being depleted of their majority carrier. So width of depletion layer will increase here, no? Width of depletion layer will increase. Agree this? So at the width of depletion layer increases. So this about this what happens here. Now what happened to most this one energetic electron, as they're able to cross still. Earlier what happened, say like a without bias 100 were crossing. Now as I increase bias, around 50 may cross. As I keep on increase bias, what happened, the most energetic electrons they find more difficult to cross from N to P type. The most energetic hole they find more difficult to cross from P to N type. So definitely what happened to this current, as I increase the bias, the width of depletion increases. As the width of depletion layer increases, what will happen to barrier potential will increase, and what will happen to electric field strength will increase. So here O will dominate here. If you look at the electric field, it should be like this, the equation. The ratio of such that the E will increase. If E increases, what happens, more retarding force for the majority carriers. So the number of majority carriers crossing the junction keeps on decreases here. Okay, able to get this? Okay, let's come for the drift current. What will happen to this? As the width of depletion layer increases, then more number of covalent bonds will break up. I'm not saying temperature. So like if the width is, say like this is say 10 micrometer, in 10 micrometer 1000 covalent bonds will break up here. Then in 20 micrometer, more number of covalent bonds will exist and more breakup will occur. That breakup making and breaking up is a natural phenomena that occurs in semiconductor. So how you have to put it, like the width of depletion layer means if for 10 micrometer, say let's say like a 1000 covalent bonds will break up here. For 20 micrometer width depletion layer, then more number of covalent bonds should break up. If more covalent bonds break up, if more covalent bonds here breaks up, I'll show some other color. This is okay. Agree this. It will be. And what about the hole? The hole will flow here. And now the covalent bond can break up here also. Not only there, it can break up here also. Let me show it. Covalent bond, or I'll show it here. No free electrons. Already see, like there is a minority carrier, this will be there, and breaking up this one. So what is the minority carrier current? Both this one, these carriers as well as this together is called as a drift current here. Okay, don't think that only this is called as a drift current. Due to movement of molecule, due to all three only, it's a drift current. No, even this whole also will contribute drift current. I'll so now we'll do one thing. I'll give name. One we took it, no. Two will write it. Three. This all four. Okay, three we took for there, no. 3, 4, 1, 2. Okay, this is 5. You write it. Let me come in order. I think there I took 3, no. 3, 1, 2, 3, 4, 5, 6, 7. Okay, now what is one most energetic majority carriers? S. They will try to cross, but their number will decrease. What about 2? 2 will not move. How 2 will move? Even for 2 also, I had to show like this. But this is not like a majority carrier. Majority carrier I'll show by red color. Once this electron comes here, once this electron from depletion layer comes here, what will happen to it? It will become what like? Majority carrier, or what you should call that one. So it is nothing but minority carrier only. It is started moving like this, no? Okay, that majority minority time being, okay, I'll suspend that. Okay, this electron also will move. Then these electrons also will move. There's some most energetic, they'll try to move. The same thing all. There's a minority carrier. From N to P type, it will move. And similarly, there'll be electrons from P to N type, they'll be moving. And this electron either generated here or here will be moving here. So any electron generated here in this region, anywhere here, how do it will move? It will, you have to say that it will move away. Don't say that, sir, this electron is moving toward junction. These are minority. This electron which are here, they are majority here. The electrons which are coming from the other than this region, all they will come become minority. Okay, clear this one. So this is what happens here. Able to get this? So shall we put like this here? As I increase the bias, first thing, what will happen to the depletion layer? Without depletion increase, how do it will increase? Because as I increase the bias, the battery will pull the majority carriers away from the junction. The battery will see that the majority carriers will move away from junction. How that happens is what I shown here. Let me keep this all for him. Finish all. The without depletion, as without depletion, more covalent bonds will break up. More covalent bonds will break up. More minority carriers now they're moving across junction. Tell me like which will be greater now. So if I go and check it now, the I drift will be greater than I diffusion. Are able to see the red color line and the green and the violet color line? So I'm only showing two lines here. What about here? 1, 2, 3, 4, 5, 6. Definitely which current will be more? The drift current will be more than the diffusion current. And this is called like a reverse current. How the current we have to show it? What is the direction of this reverse current? Opposite to this electron only. So the reverse current here should flow in this direction. High R. And this is called like a minority carrier current. This is purely due to diffusion. The diffusion will be greater than the drift here. Okay, no, we'll summarize things. That is about the story. Like the first thing as bias. This is called like a applied voltage or bias. BR or reverse bias. As reverse bias increases, majority carriers move away from the junction. They're the first thing. But sir, you are showing that these are the most energetic. Due to thermal agitation, they're moving. The sequence is what you have to show it. Okay, agree this one. The sequence is what you have to show it. I'll show the like black color one. Fine. Or as the reverse bias increases, majority carriers move away from junction. Then next, width of depletion layer. More width of depletion layer increases. There will be increase in breaking up of covalent bonds in depletion layer. Okay, there's one thing. Now, because of this, minority carrier current or drift current increases. Okay, find this one. So there's a one major reason what we can put. So if I plot the graph, let me go for the graph here. When I plot the graph what is showing is there's a reverse voltage, reverse bias, and there's a reverse current. This will be in milli or microampere. Okay, time being, let me write only IR. So the two parts of graph is what you have to put it now. So till here is one. Afterwards, a sudden large change in the current. This I'll call as breakdown voltage. So this called like a reverse saturation current. Till here, what happened? We'll call this as like a I saturation. Like what I wrote no earlier. What is the order of this? This will be of order how much? Of 10 to the power of minus 12, 10 to the power of minus 9, or 10 to the power of minus 10. So what is the reverse saturation current? This will be of order. Why? Because minority carrier, no? Though number of width of depletion increases, more covalent bonds break up, still when you go and check it, no, this current will be of order, how much will be of order? 10 to the power of minus 9 ampere or microampere, like that. Very small current, especially this is a very small current. This I saturation, how much you can put practically around of order micro or nano ampere. In books, they just put 10 to the power of minus 10 ampere. Okay, fine, justify. So definitely it's of no use, S no use. But you see that one, I have put some sudden, no, again, why suddenly current increases? You look at this. So there are two things are there. You have to make observation. Look at this part. Suddenly, as I keep on increase the reverse bias, at one point what happen? A large current starts flowing. Curve. I'll put it in exact shape. No need. Just you can put some rough curve. I think till here I have to put it. Just show some slope here. Let's have. Oh, now take it like this here. Got it, no? This will be, I think, some. So here, there's a very small of order 10. See here again, as I keep on increase reverse bias, suddenly what happened? You can see that one. Suddenly, I'm using was suddenly. What is the breakdown voltage? Let's say 10 volt, 9.8 volt. The current is of order 10 to the power of minus 10. Suddenly, when it becomes 10 volt, a large current. And if I go for small change from 10.1, the current from almost say some 10 to the power of minus 10 ampere will become suddenly 10 milliampere. Very large current will flow here. And the diode, if it is not designed properly, it will burn out. Ordinary diodes will get damaged. What I mean by damage? You'll get a smoke. It'll become ash. Large amount of heat will be generated and it'll get damaged here. This is called a breakdown. So what is that breakdown phenomena? How do it occurs? Is what we have to explain here. Now, as the voltage increases, so let me take this diagram. Yeah. Okay, let's get into this one. So as the increase the reverse bias, the breakdown, the width of depletion increases. As the width of depletion increases, more covalent bonds will break up. As the covalent bond breaks up, even what will happen to the electric field will increase. Now the electrostatic field is so high that what it will do is like it will make the charges to accelerate now. It will make the charges to accelerate. Okay, I'll switch off my phone. It is troubling me. No, let's get into this one. So as I increase the reverse bias, the width of depletion increases. As the width of depletion increases, then the amount of charge present, the charge layer in the depletion layer will increase. Let me give some symbol X here. This one. So let me summarize here like that. As VR increases, X will increase. Okay, as VR increases, X will increase. Okay, fine. This is as X increases. So what will happen to the charged layer? The charged layer in depletion layer increases. As the charged layer in the depletion layer increases, then what will happen to, we know electric field. I think I should write this is E plus, I'll write it. Sigma by epsilon naught or sigma minus of epsilon naught here. Just okay, no, sorry for disturbance. No, okay. As reverse bias increases, X will increase. Now, this X is something very important. X is width of depletion. I'm showing in the diagram. Then the charge layer in depletion increases. We know that more number of this blue color circles without ions will increase. No, the charge layer in depletion increases. If the charge density increases, definitely what happen? E will increase. If E increases, so what will happen to these electrons, the minority carriers? They'll experience a large amount of force, no? So let's get into the topic of this one. So what will happen is, how that breakdown occurs is what I'm going to give explanation. So as this, no, and this particular breakdown occurs due to thermal agitation. Due to thermal agitation, breakdown occurs. So because of that, what we get with respect to thermal agitation occurs. Due to first thermal agitation, breakdown occurs. No, now there's an electrostatic field is there. So how this electrostatic field is acting in this direction? So what this electrostatic field will do? I'll put it here now. It will exert a force towards right now on the electron. So this electron will experience a force in this direction, this electron. What about hole? Hole will experience force like this. This electron now will get accelerated. F equal to QE into E. This accelerating electron, the electron get accelerated. This accelerating electron, what it does, it will go and strike another covalent bond. This accelerating electron. So when it strikes another covalent bond, so here what happened? That covalent bond will break up. Now this electron will go and strike another covalent bond. It will break up. Again, this electrostatic field is present. In the depletion layer, I'm showing it. So this will again further accelerate. Tell me, like, you see what's happening? Like this, a chain reaction again further like this. Like this, I have to keep on draw diagram. Anybody interested, you can continue for so many things. I'll stop it here. What's happening? So, some sort of chain reaction. Like this, you can keep on. Again, this will go. So one electron here, what happened? So here, this one electron. So what is doing? Producing large number of electrons. No, this is called like a Zener, or so like it's like an avalanche breakdown. What do you mean by avalanche? Avalanche. I'm using word avalanche. So this entire diagram correspond. Avalanche, all of you, avalanche. Avalanches occurs in Himalayas or in northern or southern hemisphere. So what actually avalanche means? If there's a hill, snow, like a snow, that one hill. If a small balls, if they start rolling, so as it rolls open, it will pick up the ice, and the size will become big. By the time when it comes to the almost at the down of the hill, no, it become very big size. What is the big size? It can be of diameter of 50 meter. When this what happen when goes and collides, no, definitely large of lot of damage. It may start with size of cricket ball. This at the top of the, as it starts rolling, no, it will pick up the snow, and what it does, it will further make the other balls to roll. Not only this bigger size, you can get plenty like this. You'll get some 10 or 15 big size snowballs. That one, that's called like avalanche. One ball what pen will make the two, it'll go and will make other two balls like that. What happen, you'll get an avalanche here. So almost all this ill what will happen within some fraction of time will collapse. Fraction of time it will collapse here. This is called like an avalanche here. The same thing happening here. So one electron what happen will liberate millions of electrons. Suddenly what happened? Now a large number of minority carriers will flow. What will happen to large number of electrons? And any electron flows what happen will be pulled like this, no? Will be pulled. And there'll be what happen? A reverse current. A large current will flow. That's why the graph. Are you getting the idea? So shall I say breakdown occurred? What do you mean by breakdown? As we increase the reverse bias, the width of depletion increases. Width of depletion increases, then the charge, the amount of charge present in P and N region, this will increase. More charge, more electric field. Now the electric field is such that any covalent bond that breaks up due to thermal agitation, so the electrons which are liberated or the carriers which are minority carriers which are liberated, even the hole also will accelerate. I am not showing it because you'll get confused here. Even the old what pen will go and will strike covalent bonds. In this direction what pen, again more covalent bonds will break up due to movement of holes in this direction. More covalent bonds will break up due to movement of electron in this direction. Agree this? So that's why I'm showing for both hole as well as electron here. Like this what happen, an avalanche will occur. A large number of minority carriers will flow and a large current. How much earlier it was? 10 to the power of minus 18. Here the order of current will be of milliampere. That's why I have to show it here. That IR we show like this in book. So here this is of order 10 to the power of minus 10 ampere. Here you can put it almost 40 milliampere. Look at the current. Very large, no? And because of large flow of current, it will be generated and the diode will burn out if it is not properly designed. Ordinary diodes will burn out. That's why you should never operate in breakdown region. So usually breakdown region, how much it will be around 10 volt we can put it. The breakdown voltage. Who will determine the breakdown voltage? For some diodes, if you take this one, a Zener diode will be 10 volt. For most of the ordinary diodes will be around 20 volt. More than 20 volt will make it. Who will determine the breakdown voltage? Again, the doping level. So width of depletion layer, one more important thing, doping level, width of depletion layer, inversely proportional to doping level. So by controlling the doping level in P and N region, what I can control the width of depletion. What is this width of depletion layer? Unbiased. I mean to say unbiased. This is unbiased width of depletion layer depends on doping level. This unbiased width of depletion layer will determine what will be the breakdown voltage. Is it okay now? This one. So therefore, shall we put here VBR depends on what? Doping level. By adjusting doping levels, we can control the VBR. Okay, there is only information, just remember it. Need not to bother. Okay, got this one. So this is about the avalanche breakdown. One more process will occur. What is the Zener breakdown? So in Zener breakdown, what happens? As I increase the reverse bias, then same thing. The width of depletion layer increases. As the width of depletion increases, the charge layer in the depletion will increase, the electric will increase. Now the electrostatic force will be so strong that it will directly pull the valence electrons from the valence band. If it pulls valence electron from valence band, what do you get? One hole and one free electron. So the reverse thing is what happening. If any free electron is captured by hole, we'll get valence electron. Okay, that one. If a valence electron pulled by valence band, what do you get? One hole and one free electron. So here, so what is the next is called as a Zener breakdown. Now what we have is called like a avalanche breakdown. Next breakdown is what I'll call as Zener breakdown. In Zener breakdown, what happens is as we increase the reverse bias, I think I can write a small explanation. It'll be easier for you. First thing, as the reverse bias increases, width of depletion layer X increases. If the width of depletion layer increases, then sigma plus and sigma minus increases. Then we know that the electric field is contributed by sum of both. No, actually, depends on both. Or if you want, you can write plus because you know electrostatics. This one, I think I'll write plus here because again, no. And now E will increase, so E increases. Now come for this one. So this is the covalent bond. So what this, I think, okay, I'll give one small diagram here. This is a covalent bond. This is the electric field. So this covalent, these electrons open, they'll be binded, no, by covalent bond force. So I'll covalent bond force, I'll show by this one. Now this electron, they'll experience a force. I think I have to draw a bigger diagram. And just is a diagrammatic explanation to make you understand. Okay, there's a covalent bond. There's a valence electron. It will be binded. No, there's an electric field. It is increasing, no? Now the value will be such that at one instant what happens, this Fe will become greater than covalent bond force. What is this Fe? Fe is equal to QE into E. When Fe becomes greater than FCBV, covalent bond force, then this covalent bond will break up and then we'll get a hole. Directly it will pull up. Like this, what happened? From millions of covalent bond, directly this electrostatic field will pull the valence electron from the valence band. And it plays in conduction band. What do you get if electron jumps from valence band to conduction band? We get one hole as well as one free electron in the conduction band. Now this electron, if it makes a transition here like this, so what do we get in place of electron? We'll get one hole as well as one free electron. I don't know how to show this. Okay, I think here I cannot. At the most, I think I can show this much. If valence electron, who will pull up this from the valence band? This particular thing. So as the electrostatic field in the depletion will directly pull the valence electron from valence band to conduction band. If electron jumps from valence band to conduction band, it will become free electron, and vacancy created by valence electron in valence band will become hole. Like that, what will come? Like that, what happen? This electrostatic field in the depletion will directly pull the valence electron from the valence band, and will get a large number of, again, minority carriers will be generated and the current will be more. This is a Zener breakdown. I think avalanche breakdown, Zener breakdown, two different phenomena. Now you ask question, sir, which one will occur? For lower voltages, so means first, actually, if you take the reverse bias, no, this one. So here, let me put it here now. So as E increases, so next what will happen? So so E increases, this high electric field will directly pull valence electrons from valence band and place it in conduction band. Okay, the main reason, the last one, place it in conduction band. As a result, a minority carriers are generated. Not one, millions of, like this, millions of covalent bond, the electrostatic field in depletion layer. Where do this occur? Everything in depletion layer are generated in depletion. Suddenly what happened? The electrostatic field will start pulling the valence electron from the valence band. So we'll get one free electron, one hole. So like this, millions of minority carriers generated, a large current flows. Next question comes, so which will occur first? You have to ask question, avalanche breakdown, Zener breakdown. Ordinary diode, both will occur. For Zener diode, what happen? They'll be designed such a way that one after the other will occur. So I'll give the graph. There's a graph, we can take it. Only red color should be there. This is the Zener breakdown. This is a avalanche breakdown. For some of the diodes open, they are designed in such a way that both will occur simultaneously. Usually Zener breakdown first will occur, then avalanche breakdown. Go this, and for some of the diodes, both will take place simultaneously. So nothing wrong. Huh? You can just this one. So this is called like a breakdown. So if they, what's happened to diode, ordinary diode will burn out. Usually this breakdown voltage will be adjusted for 20 volt for ordinary diode. For Zener diodes, next what we did, take the applications, no, it will be adjusted for lower values. Can we adjust this breakdown voltage? Yes, it depends on doping level. This is what happens in the reverse breakdown. This one, so avalanche breakdown, and this is very important. Okay, this is about the theoretical idea of the reverse bias. Any doubt, if you want, you can clarify, because this completes the conceptual part. Here afterwards, what we do is numerical. Doesn't need all this one. Huh? Doesn't need all this one. Means in numerical, what actually happens? If a diode is forward biased, what to do? How to do the problem? If the diode is reverse biased, what to do? What to do with this problem? So if the diode is forward biased, depletion layer is minimum, almost